Okay, we continue. We're still in section 3-4. As I've looked at this section, I think we can finish it off. I do not anticipate that you guys will have a test before Thanksgiving. If you did have a test before Thanksgiving, I'd probably have to modify it and have it be some sort of take-home test. But I do not anticipate that. So right now, I plan on you guys having a test shortly after Thanksgiving. This is the earliest that Thanksgiving can be. The 22nd is the earliest that Thanksgiving can possibly be. So, anyway, here we go. Let's see what you've learned from your 6 problems. Boys, girls, again, I know how to do all of these problems. You don't know how to do any of them yet. So, all right. I'll watch it before lunch. Let's see what you guys remember about what you've learned on, Monday. I'm sorry, last week, Thursday and Friday. And Wednesday we talked about velocity. We've talked about change of direction. This says as follows. A ball is thrown upward with an initial velocity of 18 meters per second. The height of the ball is modeled by the equation h of t is equal to 18t minus 4.9t squared. What is different about this problem compared to the problems that we looked at before? Okay. Tells us not the velocity, but the height. Oh, yes, it does tell us the initial velocity. I'm sorry. Yeah, so if the problem asked, what is the velocity at time 0, you would know that right away. Okay, so very good. That is one distinct difference. The other piece is that we are looking at height. So I suppose instead of looking for a particle of motion on the x-axis, we're looking at the height on the y-axis. Now, we don't know horizontally where it's displaced. I mean, I could throw a ball from here over to Curry, and it would definitely have height, but it would also have horizontal displacement. We do not know the horizontal displacement. We only know the height as a function of time. So, what is the maximum height that the ball reached? Question. That means that if I throw a ball into the air right now, let's say I throw it to Curry, the maximum height would obviously be the distance from the ground to the height of the ball. The horizontal displacement would be if I'm at 0 on the number line and Curry's at say 27 on the number line, 27 feet would be the horizontal displacement. So how far the ball went horizontally, not just vertically. Okay. All right. So maximum height the ball reached. Any ideas how we would figure this out? Very good. I could do negative b over 2a. Let's use calculus. I throw a ball up into the air. Is the velocity positive on the way up or negative on the way up? Positive. I throw a ball up into the air. Is the velocity positive on the way down or negative on the way down? So if there's a change in the velocity from positive to negative, at some time the velocity must be equal to 0. And it's equal to 0 at the maximum height of the ball. So in order to find the maximum height, we simply the 0 of the velocity. The velocity with respect to time is equal to what? What do? I take the derivative. So v of t is equal to 18 minus 9.8t. I take the derivative. That will tell me the velocity at any given point. So just like Marlene said, she said that we know the initial velocity is 18. Well, yeah, if you plugged in 0 into here, you would get a result of 18. So it works out. It matches with the problem. Now, the other part of it is that we want to know exactly when the velocity is equal to 0 because that's when it changes direction. That's when the ball gets to its maximum height and it's on its way down. So we will say that 0 is equal to 18 minus 9.8t, or 9.8t is equal to 18. If I divide both sides by 9.8, I get 1.84. $1.84 what? What did I just solve for? It's the time. After 1.84 seconds, the ball has reached its maximum height. The question asks for what is the maximum height. Have I just found the maximum height? I've only found the time at which it reaches the maximum height. How will I find the maximum height? Do I plug it into the velocity function or the height? I plug it into the height function. And so I take 18 times 1.84 minus 4.9 times 1.84 squared. 16.53. Yep, 16.53 meters. Now, Andrew is exactly correct. We covered it in pre-calculus today. In order to solve that problem, you could just find the vertex and do negative b divided by 2a. However, you do need to have the derivative in order to do problem B. And problem B says, what is the height of the ball after 2 seconds? What would I do there? Plug in 2 to what? Right. V of 2 is equal to 18 minus 9.8 times 2. So the velocity at time 2 is equal to 18 minus 9.8 times 2. Instead of V of t, I just plugged in 2. And I get, question? Yes, yep, I plugged in. In order to figure out the 16.53, I plugged 1.84 into the height. Oh, I'm sorry. I'm sorry. I read the wrong one. I'm sorry. We'll just I was reading was the velocity after 2 seconds. The question was the height after 2 seconds. I read the. Yep. So can we boys? Can we just finish this part right here then? Should we just switch them? Okay. And we'll just erase everything. So, V of 2 is equal to, again, we said 18 minus 9.8 times 2. So that's 18 minus 19.6. What's 18 minus 19.6? Negative 1.6 what? Very good. Since I'm solving for velocity, I have meters per second. Does it make sense that at 2 seconds it would have a negative velocity? Why? Because the velocity is 0 at 1.8, so then it's going to be on its way down. So since 2 is after 1.8, we know that it's going to have a negative velocity. Very good. If I wanted to know the height of the ball after 2 seconds, I would plug that into the original. So h of 2 is equal to 18 times 2 minus 4.9 times 2 squared. And what do we get? We get 36 minus 4.9 times 2 squared is 19.6. Which equals 16.4. 16.4 what? Meters. That's our height. That's our velocity. Do they match up? Yep. Does it make sense within context of the problem? Yep. Okay, and problem D, it says, at what time does the ball have a height of 20 meters? Very good. So I would use my original function, which would be height. So 20 is equal to 18t minus 4.9 times t squared. Now, as already noted by Ben Jones, it won't reach that height. Okay. Oh, did Chrissy say it? As Chrissy said, it's not going to reach that height. We know the maximum height is only 16.53. So therefore, it can't get up to 20. So if we solve this with the quadratic formula, what should we come up with? An imaginary solution. And if you subtract that 20 over, or if you add the 4.9 over, however you want to do it, 4.9 t squared minus 18t minus 20 equals 0. If you do plus 20, if you do in fact plug that into the quadratic formula, you're going to get an imaginary result. Yep. Once again, and if I have time at the end of today's lesson, which I might, I'll print off, again, the quadratic formula sheet so that we can plug in our calculators for those of you who need it. So never reaches 20 meters. Okay? Now, let's just switch the problem for a second. What if the question was, when does the ball have a velocity of -2 meters per second? What would you do then? Yeah, I would set the velocity function equal to -2 and then solve from there. Okay? Any questions? Okay, these are very similar to the problems that you did last week. They're also very similar to things we've encountered last year. Now it's time to try something entirely new, okay? Same type of process, but we want to extend our learning just a little bit here, okay? So this is going to be problematic for us unless we really follow along. So let's watch this. Boyle's law. Are you guys familiar with Boyle's law? Okay. Pressure times volume is a constant, remains at a constant. And another variable that can be expressed in there would be temperature. For example, if we heat an object up, generally it will expand, especially if you heat a gas up. Now, in this problem, we're going to say the temperature remains at a constant. So Boyle's law states that when a sample of gas is compressed at a constant temperature, the product of the pressure and the volume remains at a constant. P times V equals C. Now the problem with this is that you guys don't see any numbers in here, and it makes it look kind of difficult. The first question is, and you guys, by the way, this is exactly like the question that you have on your assignment. I have one like this. And you're going to be doing the same exact stuff. I just want you to understand why you're doing what you're doing. So let's try to follow this. It says, find the rate of change of volume with respect to pressure. Find the rate of change of volume with respect to pressure. So if I'm finding the rate of change of volume, I'm looking for the, I heard somebody say it, derivative of the volume. Okay, so let's start by solving for the volume. Okay, the volume is equal to C divided by P. True or false? The volume is changing. True. True or false? The pressure is changing. True. True or false? C is changing. False. That's a constant. It's a number. So for example, the pressure times the volume could always be equal to, say, 10, something of that nature, okay? So we have this formula, okay? This is just some number. I'm going to rewrite it for you and see if this makes sense. This could be equal to C times P to the -1. Does that make sense? So if we want to find the rate of change of volume with respect to pressure, I would say that V prime, if I take the derivative of it, V prime negative C e to the negative 2. Very good. Or negative C over P squared. Does everybody understand how I got that? Okay. Ella. Then we're going to Ella right here, okay? I have CP to the negative 1, okay? Do you see how I have that? Okay, so this is just a constant, like 2p to the negative 1. So if you took the derivative of that, you would bring the negative in front, right? And subtract 1 from the exponent. Got it now? Okay. So there's my derivative. If you want to know the rate of change of the volume, you simply take negative C and divide it by whatever the pressure is squared, and that will tell you the rate of change of the volume. Now, let's try to understand the more difficult part. A sample of gas is in a container at low pressure and is steadily compressed at a constant temperature for 20 minutes. Okay? So it's steadily being compressed. So it's like a balloon. You're pressing it closer and closer and closer together, okay? All right? If I have a balloon and I start pressing on it, what's going to happen to the pressure? It's going to increase, right? The pressure is going to increase, okay? Now, it says, is the volume decreasing more rapidly at the beginning or the end of the 20-minute period? Well, let's think about this for a second, okay? The volume prime is equal to negative C divided by, at the beginning, is the pressure going to be big or small? Small. We're hardly compressing it at all, right? So let's just put a smaller number there. Let's just put 1. Okay? 1 to represent a smaller pressure. Let's then try something else. Well, we'll say after it was squared, it was 1. Doesn't matter, okay? Now, let's say that, the pressure is increasing, okay, because we're continuing to compress it. Negative C over 2. Let's say even later, we have negative C over 3. Does everybody see that the pressure is increasing? Now, think about this. If you take negative C and divide it by 1, and then take negative C and divide it by 2, and take negative C and divide it by 3, what's happening to these results? It's decreasing less rapidly. Okay? So if you have, say, negative, so it's going to be the rate at which the volume is decreasing, right? Because it's negative. It's happening more rapidly here. It's happening less rapidly here because you're dividing by a bigger number. So that result is going to be closer and closer to 1. It's decreasing more rapidly where? At the beginning or the end? Yes. Okay. So Taylor, you ask a really good question. So I know that some people out there, you're thinking of what's actually physically happening. It seems obvious to you. Let's do two things to push this together, okay? Let's suppose that I have a balloon, okay? And I compress it, okay? Is the volume, as I start pressing on it, think about it, okay? As I continue to apply pressure to it, okay? what's going to happen to the volume right away? It's going to decrease right away, right? But there's going to be a time where even though I'm pressing, the volume is not going to change so much after a while, right? So the volume's going to become a lot less right away as I press that balloon together. Now think about this. You could just plug in numbers here. Let's plug in. No, I mean, we could just plug in whatever, but let's suppose that C was 1. Then you would have negative 1 over 1. Then you would have negative 1/2. Then you would have negative 1/3. So the fact of the matter is you can see it's decreasing more rapidly, a greater rate right there as opposed to down the line. And it doesn't matter what type of numbers you plug in, you're going to see that that would be true. And that's the process of trying to kind of understand it. Does that make more sense? Okay. All right, last example. Yep. Okay, so you've seen how derivatives can play a role in motion of a particle, an object being thrown up into the air, Boyle's law. Here's another example, and it's in economics applications, okay? And so the cost function is as follows. Okay, we're going to identify a cost function to be C of X. Boys, please, whatever you're talking about is much less important than what's happening right here. Total cost a company has in producing X items, C of X. Okay? We're going to identify that as a cost function. In economics, something that's of great interest to them is the marginal cost function. And the marginal cost function is the instantaneous rate of change of cost with respect to the number of items produced. That makes it the derivative, or C prime of X. It relates to supply and demand. I'll make that connection here, but not necessarily. Approximately, right somewhere else then. The cost of producing one more item. C prime of n is approximately equal to C of n plus 1 minus C of n. Now, we are going to get back to economic applications as we kind of move along in this course. This is the introductory piece, and you're not going to do anything today that is very difficult. However, you have to understand what's going on. You have to understand what's going on. Okay, so we'll let you write that down, and then we'll talk about it. So I'll give you a few more seconds here. Yep, C of n on the end. Yep. C of x. Yep. Sure. So, all right, let's understand this, okay? I'm a company, and I just get started. Who wants to make something someday? What product would you like to make? Yeah? Okay, very good. Okay, so Katie Williamson is going to go into business. She is going to produce a potluck plate. And the reason why she wants to do this is because when you're at a potluck, which not many of those, I mean, it's kind of a Minnesota thing, is it not? Midwest thing. Okay, so as we go to these potluck suppers, there's a lot of really great food. But there's two issues. Number one, do you have room to put it everywhere? And number two, you don't want it all to like get mixed up with each other, right? Because that's kind of gross to have your orange Jello mixed in with your goulash, right? I mean, you don't want that, all right? So Katie produces, okay? She's going to produce this. Tell me, what is her initial cost in order to produce these? What does she have to consider? She has to consider materials. What else? Packaging, advertising, labor. And she also has to consider the actual tool, the cost of the tool that she's going to use to manufacture these. So, for example, let's suppose that Katie was to go into business. Would it be smart for her to go into business to produce these potluck trays and make two of them, one for her and one for Greta? Ella, why would that be stupid? Okay, well, we won't talk about profit yet, but let's just think about cost. Ella's got a good point here. You want to just produce a bunch of them. Okay, now if let's say that they just had, that they just produced two of them. Would their cost be a lot per piece or a little? Be a lot. Now, let's suppose that they decided to try to run an efficient business and they did hire people to work and everything, and they hired good people. Would it cost more? This is tricky, you guys, okay? Would it cost more to produce 1,000 items or 2 items? It's going to cost more to produce 1,000, but the rate of the cost, is the rate of the cost going to be greater for 2 items or for the 1,000th item? Okay, the 2 items, the rate is going to be extreme. The 1,000th item, the rate is going to be much less. That's what marginal cost is. It's that rate at which the next item is produced. And they want to find that rate because at some point it's going to be worth their while and some point it's not going to be. There's a spot that they're very interested in. We know that they should not produce just 2, right? But how many should they produce in order to make it worth their time and effort? That's a whole nother question, and that's very important to know, and we'll look for that later on. But right now, we need to study marginal cost. So, company produces X number of shoes. The cost can be estimated by the following function. C of X is equal to 10,000 plus 5X plus 0.01X squared. The question is, what is the marginal cost function? What do I do? I take the derivative. When in doubt, find the derivative. What is the derivative of that? Five plus 0.02x. What is C prime of 500? How would I calculate that? Plug it in. C prime of 500 equals 5 plus 0.02 times 500. 15. 0.02 times 500 is 10 plus 5 is 15. 15 what? So $15. Sure. Okay. Now, interpret what C prime of 500 means. What does that actually mean? Now, hold on, you guys. Hold on. I want to make sure that we're clear here. This does not mean that the average cost of producing 500 items is $15 an item. It is going to be more than 15, definitely more. What it means is it will cost approximately $15 in order to produce item number 501. That means in order to produce the 500 first pair of shoes, it's going to cost about 15 bucks to produce that pair of shoes. Now, if we go back to Greta and Katie's scenario, when they started out at the beginning, it maybe cost them, maybe cost them $400 just to make the, first two pair of shoes. But over time, it's slowly evening out here. Okay, so here's what we want to do. Okay, we found that C prime of 500 is $15 an item. Okay, let's compare C prime of 500 with the cost of actually producing the 500 first item. What's that? Oh, right here. Because it's the next item. Talk about producing the next item. So, here's what we know. C prime of 500 is equal to 15. Well, we know that that is approximately the cost of producing the 500 first item. So what I'm going to do is I'm going to figure out what the cost is of producing 501 items. And then I'm going to subtract off the cost of producing 500 items. And that should give me the cost of producing that next item. Does that make sense? So, before Katie and Greta know how to do calculus, they're like, boy, I wonder what kind of rate we're producing these at. What kind of cost we're incurring. So they're like, well, let's just figure out the cost of 501 and subtract it from the cost of 500. That'll be about the rate. That's not instantaneous. That's using 2 points, right? But it's going to be approximately the same. So let's figure these out. Let's try 501. We'll plug it in. Into the original. 10,000 plus 5 times 501 plus 0.01 times 501 squared. And I get 15,015.01. So that's their cost. That's their cost to produce 501 pair of shoes. 5,015.01. Or 15,015.01. So now let's figure out how much it's going to cost to produce just 500. Well, 500 would be 10,000 plus 5 times 500 plus 0.01 times 500 squared. Curry, question. Boys and girls. Shh. Curry, the question is, why does the 0.01 cancel out? Because here's what we're doing, Curry. Very good question. Okay. So Curry's wondering why what happens with the 0.01. As you can tell, these don't match up. Here's why. Okay. That's point number 500. That's point number 501, right? 15 represents that slope at the tangent line, right? 1501 represents the average rate of change between these 2 points, which is just slightly different. Yes, difference of slopes of the two. They're extremely close, and it's a way for us to check to see that our answer is within reason. Does that process make sense? Now, finally, last piece is this. You guys said before, you made the mistake. Somebody said, well, on average, it's costing them $15 per shoe. No, if you look, they've spent $15,000 to produce 500 pair of shoes. If I divide that by 500, you can see that they're actually on average spending so far $30 per pair of shoe. Now, you see what I'm saying? So, so you can't say that 15 is the average. It's the instantaneous rate of change. Okay. That's the cost to produce the 500 first item. No. I will explain that to you. Okay, here you go. So, A and B, there's a part C there. Don't do part C. But those are ball into air problems. This is a Boyle's problem. Those two are econ problems. That one's just slightly different. I'd like you to see if you can figure it out. Good luck.